Firstly, did anyone already see this talk? Because I think it a few weeks. Great. This is fun. Okay, so the structure of the talk will essentially I'll give a brief introduction, and I had planned 3 case studies, but I won't call them these two. Okay. You're welcome to ask me about case study 1 later if you're interested. But let's get started. So the topic today is potential lower bounds and impossibility results. Has anyone heard this term? By the way, I love interactive discussions, so yeah, you don't have to like wait for me to ask a question. If I ask a question, it's great. So yeah, does anyone, what do you understand when I say lower bound? Yeah. Yeah. Yes, and in fact, when I gave the talk last time, someone gave very similar. Yeah, that's actually right. Okay, it's some kind of like, yeah, an integral. I guess it's like the lower bound of the integral, what you're talking about. In general, when you say something has to be at least a certain value, that's called a lower bound, right? The object probably looks in it. Like you say x is at least 2 is lower bound. Computer science gets used in essentially the same idea, but not what very specific quantities, particularly resources that are needed to solve problems, right? So when I talk about low bounds computer science, you say, well, if I have to write an algorithm for this particular computation, it needs to take at least so much time, at least so much space, right? Or in the farthest setting, and when it gets to an impossibility result, you're trying to say something like, in fact, no algorithm can solve this problem, right? So some examples that you've seen and may not have connected or may not have seen. The first one is the pigeonhole principle. Everyone's seen this, yeah? Right? So you can view it, I mean, it's a simple statement that there are some possibilities, right? And it's kind of obvious, and you encounter this, and you probably might have already seen that a simple tool such as this can prove very, very complex things. And that kind of holds true even in computer science. In fact, the first case study we would have done, which gives you a broader, surprising conclusion, I might say at the time, is proof using something as simple as using a counterpoint, right? So it's extremely powerful, and in that sense, it in itself can be viewed as a lower bound. It's an impossibility result, right? It says that if you have n plus 1 pigeons, you can't put them into n pigeonholes. Other things that are closer to computer science that you might have seen, everyone knows the problem of sorting n numbers. And you probably encountered many different kinds of sorting algorithms, and you know they all run time and log n. You might have also seen that sorting requires n log n. Okay, so that's a lower bound. And the last one, which again, you might have seen in a different format. Who's heard of all? You've heard of it? Sort of? Sort of, yeah. It's actually a very simple problem. It says, if I give you an algorithm and an input on the difference, can you tell me if the program will ever fall? Right? It turns out, in general, the problem is unsolvable. There's no way to do this. Its proof was actually quite elusive, and in fact, just as elusive as does everyone know the story behind understanding whether the real numbers are countable or not? Okay. Well, the TLDR is for a long time never thought that didn't work. It's very true that if you go on some account, you can assign formally there's a bijection from a set of natural numbers to the given account. It just means you can say this is first element of your set, second element of your set, third element. You can enumerate. And so obviously the natural numbers are countable because the bijection is just identical. And then you can set up clever bijections to the integers irrational numbers, and so on. But then we did the next irrational reveals, and for a long time it was believed that they could also be counted. And then Cantor showed using what's known as a diagonalization argument. Have you heard this term? Doesn't matter if you're not. I'm just trying to connect dots if you have. He showed that they weren't countable. And the miraculous thing is something which is in the depths of real analysis, so to speak, can also be applied to computer science and show that testing of a program calls on an input is also impossible. It's essentially the same one. Right? Okay, so fine, that's impossibility results. The question one would want to ask is then why should we care? Sure, these sound cool and all that, but why do I care about proving these kinds of results? Like, yeah. So your program doesn't take forever to run. So this is assuming I've written a program for something like this. Okay. All right, can you explain a little better or exactly?
Well, I guess you don't.
Yeah. So sometimes you want to know if it's pointless. Right? If I tell you, hey, solve this problem for me, sometimes you want to know that it can't be solved. Because otherwise you're going to break your head like Cantor did for a very long time. Right? So I like this picture of this idea of Icarus. But it's important sometimes to know what cannot be done before you can actually pursue something that can't be done. So yeah, that's one reason, and probably the reason that's most evident to you now. Hopefully, there are many other reasons because the study of impossibility results is somehow fundamental to the theory of computer science, right? So they reveal very important structural properties of the problems that we're trying to tackle, and not just show that something cannot be done. Sometimes they will show that some things can be done. And my area of research, which is cryptography for the most part, has very surprising results. Like for instance, if some particular lower bound holds, then I can construct it. If the lower bound doesn't hold, then I cannot construct that. Right, so it bridges the gap. It says, something is impossible from the top and vice versa. It's kind of interesting because normally you would imagine that, well, Pigeonhole says you can't count. That means you can't sort fast. That means you can't do something else, right? But on the flip side, you can get things like Pigeonhole says you can't, count in a certain way. Imply something else is possible. It's a little trickier and probably very hard to appreciate at this stage, but just something out there if you're interested to know about. Okay, so that's the introduction. I want to move to my case studies. Like I said, I'll skip case study 1. But any questions before I go further? All right, let's go to case study 2. And it's on coin flipping. So here's a somewhat artificial contrived scenario, but one that has a real implication in practice. So Alice and Bob want to jointly flip a fair coin. Okay. So the setting is, they're at a party. Unfortunately, neither of them has an actual fair coin with them. So they said, hey, let's work together and jointly flip the fair coin. The requirement is that the setting is, neither of them. Well, let's make it maybe a little more concrete. You and I are at the party, and we want to order dinner. What do we do? Okay, you want to order Indian, and I want to order Thai. Okay, and we want to make have a fair decision on this, so we want to flip a coin, say rather than go on Thai. Okay, but obviously you want to get to right? And I want Thai. I'm very biased. In other words, you want West Canada. Okay, so how we got to decide what to eat. All right. So the guaranteed one is that either you or I are whoever is in the end, whatever we decide, and we decide something, that can be fair, right? And we must also decide that thing. Doesn't make sense if you decide, yeah, we're going to restore that or start. All right, is that clear? So the question is this possible? Can two mutually distrusting parties jointly flip a fair coin? Okay. We often model this as, Alice and Bob, by the way, are like the poster child for crypto. There's also a Charlie, there's also a Dave, and he meeting model. So in this case, we're just going to think of this as they keep sending messages to each other, and eventually they'll decide what's up. Okay. So here's the surprising result. Alice and Bob cannot flip the coin. It's just impossible. Now, the guy will decide to do one of us identify for 8 or 5. Is this surprising? It's not good. Oh. Why not? Doesn't it just seem very sad? Isn't it really sad? You can't perform. Oh. Yeah. Yeah. So we have to make a decision together, right? In an ideal world, this decision making would be opposite. Let's say you a point, an actual, right? You topic, and it's making the decision for it. And if you believe it's a fair point, it's doing fair, right? But now we don't have the luxury of doing this, right? So we have to kind of emulate by sending whatever message we want to each other. We have to emulate the top one. Does that make sense? You can ask one question. Is that okay? Yeah. Why can't they say that again? Well, I'm kind of think about that. Maybe let me change the scenario between like a little more believable. Okay. We're not in the party yet. The regular place, I'm in my case. We're gonna go to the party. So we have to order. So if you're flipping coins, I can't see that. Okay? If I'm flipping coins, you can. Now we gotta figure out how to flip a coin. So by what you said, I can say you flip a coin and just tell me what comes up. What are you going to do with your sense? Yeah, it will say it came up heads. We're getting to here. Now, do I believe it? Yeah. You can ask the second question. Oh, I thought you no. Yeah. Yeah. Ooh, why so? You're thinking the disrupting part of it? Yeah. I'm like, we still gotta run things forward. So maybe the stakes should be higher than us will bring dinner. Right? Let's say it's actually some big part of a $1 million contract that we're negotiating. And we're trying to figure out which way to go. And if we can't decide, we're going to toss a coin and go over. Now I can't just be like, well, people are going to lie. Yes, I guess like that's the hope, right? That this should be possible. And there are real stakes like you look at bottom today where this happens. Because what will happen is, okay, let's slide second. Does everyone know about blockchains or ledgers? Yeah. Okay. A lot of blockchains, the way they're run, because there's so many people who have things on blockchain. In principle, it's totally decentralized. You want all of them to work together to update the product. Obviously, this is not on the scale. You want millions of people to decide how things work. So what they do is they will pick leaders for every round. They 3 of you figure out what's going to happen this round. And the next round will elect another set of leaders. So it's democratic in that sense, but there is some trust on some core set of rules all the time. Okay? Now, if I put this side who it was, and that person happens to be malicious offense, you can take the full. Right? So you want this leader election to be fair. You really want it to be the case that you democratically pick who runs that round. Right? So if you can't, that's a big problem. Does that make sense? Yeah. Okay. Good. Okay. Okay. Fine. Hopefully we all now believe that the problem is important or interesting. That's how it can't be done. So I guess the whole point of explaining why it's important is kind of neat, something you can't do it. There are ways in which it's achieved in practice, but in its truest sense, it cannot be achieved. Is this surprising? Not surprising. Why is it not surprising? Yeah. That's actually a very, very interesting thing to say. No, yeah. And a lot of these problems, a lot of the most fascinating forebounds are from the simplest of questions. Right? This question is so simple to state, you can say it as an argument. And then it is surprising that there's just no way to do it. Right? In fact, I kind of see why it's surprising. Something you should really try to wrap your head in that time is, well, if I close this problem to you, how could you do it in practice? That's let's try that. So we're on the phone. What are you gonna do? Like, how should we decide? How should we? Like, we're gonna try the little protocol. We're gonna break it every time. Maybe we'll make it more complex, but hopefully you'll see why it's actually hard. You're gonna ask me why. That's outside the list. I don't know what. I mean, it's not some like psychological game where they're like tricking you to watching. So yeah. Huh? We're gonna FaceTime. Oh. Let's say we don't have FaceTime. We're in the country where we don't have FaceTime. Yeah. That's just like the whole like I tell you to think about this. Okay. And like if it's even then one thing on. Okay. You tell me to pick a number, and if it's even, you see it. If it's odd, you count. Okay. I picked a number. It was 5. Is it protocol good? Yeah. Fantastic. Okay. I'll run your thought experiment, and I'll tell you what you did. Okay. If you made me, say odd or even, right? And now you're saying, well, you can't tell me odd means 5 even. So then I'll just say I want odd also. But there's a problem with this too. What's the problem? Yeah. Yeah, exactly. Because I don't know what odd and even are. No matter what I say, you're going to claim that that data is actually here. Okay. Now what? Yeah. You bring that outside third party, the whole world falls. But just like we don't trust each other, we don't trust anything. Yeah. Oh, fantastic. This is a great question. If they were simultaneous, you can actually call. So no, they are not. Yeah. So say that again, you can't come right down the format. Fantastic. So you're saying I have to essentially commit to my, like I commit to order even, or you commit to what order you need before you decide to vote, right? So that the other parties can think that you're not like after the fact deciding like, okay, what are you gonna say? You know anything about that? Yeah, but yeah. So you could like not write it down. But let's say there was a way of verifying something down, right? And actually, we can't do this. All commitment actually. In real life, maybe I send you a sealed document, but it only puts open on, or you can keep it. The issue with this, which is more subtle, and in fact, this is a real problem. I'm gonna say, you know, when you're about to decide the answer, I'm gonna say, oh, if I'm going back there. Then I think that there's some issue. I think it's good first. Does that make sense? So I won't let the protocol complete unless I get what I want and I leave. Okay, so this is a kind of like the most malicious way of causing this thing to be impossible, right? But okay, essentially, hopefully now we've gone through a few things and we're sort of convinced that there's some fundamental problem. No matter what you try to do, it seems like one of us always has the opportunity, precisely because of the lack of time. One of us learns the point, or learns more about the point. And that person can decide whether this protocol is right. So, in fact, let me just almost formally talk about this, right? So let's say these were the messages that were sent. So the first thing I observe is Bob can predict the coin after seeing AR. Right? So Bob gets Alice's last message, and then Bob should be able to do the answer. Bob should say the coin actually is, right? Maybe Alice can't and needs information from Bob, but Bob's not getting any more information from the protocol. Right? So Bob gets to up the plan again, AR should be enough. If Alice now needs BR, then Bob could bias the coin. Bob could just say, call disconnected, sorry. If it's not the coin he wants. Make sense? Okay. So if this protocol is fair, Alice should not need to see BR. Right? Okay. But that means that Alice can now predict the coin after seeing Bob's second last. It doesn't need Bob's last. It only needs Bob's second last. But then if Bob needs Alice's last message, Alice will watch Bob. Right? So then we're saying Bob doesn't need Alice's last message. So neither of them need their last messages. You can imagine what's going to happen. You just keep unwinding. You'll get to a point where you'll say, well, Bob can predict the coin after seeing Alice's first message. Which means Alice cannot need Bob's first message at all, which means Alice, without doing anything, can just predict the coin. That means the coin is not here. You can't predict it. Right? That's it. So this means that they can't flip a third coin. Does that make sense? All right. Okay. It was the time on this. But hopefully, the point I want to drive home here is that this result is somewhat foundational, somewhat has far-reaching consequences in terms of what you can achieve in practice, right? But the impossibility is strong and yet super simple. In fact, the table is written, this impossible result fits in one column of the two columns. It's just one column, that's it. Right? It's extremely simple, but this is the other amazing thing about roll bounds, is they rule out so much, and yet they're super compact. Right? We look at 3 or 4 protocols, and we know them now. There are millions of protocols we have not looked at. Maybe we can do something way more complex. Maybe you can use fancy math, right? Or think of that all the time. This says maybe we use quantum technology, maybe we can use other things. This result really does not care. It says it's just not awesome. Right? So that's another reason why you should care. The other reason why lower bounds are elusive, they're hard, they're often incorrect the first time they're written down. There have been many papers that have been published that have pointing lower bounds that were subsequently proved wrong. Right? And maybe fixed, maybe patched, a month later, a year later, a decade later, have just not been patched. Right? All these. And it's because they're so tricky that every little thing that you make has to be really stress tested. Because you're not claiming that here's something I can do, you're claiming that no matter what you do, you can't. Right? So you're ruling out things you haven't thought about. It's wider. The other reason they're sometimes interesting is they don't, a lot of the times they won't give you much more information than the task you're trying to do is impossible. Here actually it's something a little more. Like thing we learned is what's missing is simultaneous. Right? If we had that, this entire argument falls apart. And so it's a way that you could potentially bypass. And a lot of times you'll see that the argument just says that something is not possible, but if you ask what can I do to make it possible, you will say and you have to work a lot harder to actually still what you change about a problem or the approach or the model that will make something possible. Because remember, we're in a world where we want to do things possible. We want to do, we're not content with saying you can't do something. Like it's fine to know that we can't do something, but I want to know what I can. And lower bounds are not always the most informative in that sense. All right, let me skip this entire thing so that I can give you my email as I promised. There it is. But yeah, hopefully this gives you a window into the world of lower bounds. They're super interesting, super challenging, but also sometimes the correct lower bounds group is simple to cover. Well, I will get confused. Within they're accessible regardless of what level you're at. You follow a group that I introduced to you in like 15 minutes. So there's probably that many of them are actually accessible. Okay, that's all I had. Yeah, if you have questions, feel free to ask, or I guess we'll have to. I don't know what the next event is. Yeah, so, but yeah, thanks.
Awesome, thank you so much. I think that's a really interesting problem. Also got a lot of real life scenarios, but I think you're going to realize other things on my coding plus until we